What is the main problem addressed by the proposed method in the paper?
The main problem addressed by the proposed method in the paper is the challenge of enabling large language models, LLMs, to effectively perform complex, multi-step tasks that involve interactions with a realistic and dynamic environment, such as tasks in the WebArena benchmark. The paper focuses on improving the performance of LLM agents in navigating and completing tasks on websites by introducing self-improvement techniques through fine-tuning on synthetic training data. These techniques aim to enhance the capabilities of LLM agents without the need for additional supervised training data, which is scarce and costly to acquire for tasks requiring sequential decision-making and complex interactions. The paper specifically aims to address the limitations of existing benchmarks by introducing more realistic and diverse tasks that necessitate dynamic interaction and navigation in complex environments, where even state-of-the-art models like GPT-4 struggle to solve a significant portion of the tasks. The proposed method aims to enhance the performance of LLM agents on these challenging tasks by leveraging self-improvement strategies that involve fine-tuning on synthetic data and employing unsupervised techniques like self-critique to selectively filter and improve training examples.
How does the proposed self-improvement technique work for large language models? Provide a step-by-step explanation.
The proposed self-improvement technique for large language models, LLMs, works by first collecting in-domain synthetic training examples and out-of-domain synthetic training examples for web agent tasks. These examples are generated by the base LLM model itself. The in-domain synthetic examples are collected by filtering out low-quality trajectories where the model self-detected failure or where failure was detectable in the environment, resulting in a set of plausible trajectories. The out-of-domain synthetic examples are generated by prompting the base LLM model to create completely novel tasks, objectives, web pages, and solution trajectories. After collecting these synthetic examples, the base LLM model is fine-tuned on 3 different synthetic data mixtures. Mixture A, in-domain synthetic examples only, Mixture B, both in-domain and out-of-domain synthetic examples, and Mixture C, out-of-domain synthetic examples only. The fine-tuning process involves training the LLM model on the synthetic data using an auto-regressive loss function. The model is trained on a 0.9% train validation split of the datasets with specific hyperparameters. The self-improvement technique aims to amplify the model's knowledge, correct behaviors, and introduce regularization by using the synthetic data. By fine-tuning on these synthetic examples, the LLM agents demonstrate improvements in performance on the WebArena benchmark tasks. The experiments show that all 3 synthetic data mixtures lead to performance improvements, with the best performing mixture yielding a 31% improvement over the base LLM agent. Additionally, the proposed technique allows for the acquisition of new capabilities by the agent models, as demonstrated by the increase in the number of capabilities demonstrated after self-improvement.
What are the theoretical benefits of using synthetic data for self-improvement in large language models?
The theoretical benefits of using synthetic data for self-improvement in large language models include the ability to amplify knowledge, correct behaviors, and introduce regularization, leading to an overall boost in performance. Synthetic data allows for fine-tuning the model on its own generations, which can help reinforce correct actions and decisions while filtering out incorrect actions and biases. By using synthetic data, models can acquire new capabilities through self-improvement, as demonstrated in the experiments where agent models improved their performance on complex, multi-step tasks like web agent tasks. Additionally, synthetic data generation enables the model to learn from diverse and novel tasks, objectives, web pages, and solution trajectories, improving generalization and adaptability. The use of synthetic data also provides a cost-effective and efficient way to train models for tasks that lack sufficient real-world training data, as acquiring data for sequential decision-making and complex interactions can be time-consuming and costly. Overall, Synthetic data for self-improvement in large language models offers a way to enhance performance, acquire new capabilities, and improve robustness in a variety of tasks and environments.
How are the new techniques for self-improvement validated in the paper?
The new techniques for self-improvement in the paper are validated through a series of experiments involving fine-tuning agent models on synthetic training data mixtures. The experiments assess the extent to which the agent models have self-improved over the base agent model by evaluating their performance using standard metrics proposed by the WebArena benchmark, such as functional correctness, as well as new auxiliary metrics proposed in the paper. The experiments involve fine-tuning the base agent model on different synthetic dataset mixtures, namely Mixture A in domain synthetic examples only, Mixture B, both in domain and out-of-domain synthetic examples, and Mixture C, out-of-domain synthetic examples only, using a straightforward autoregressive loss. The results of these experiments are presented and discussed, showing improvements in benchmark performance, acquisition of new capabilities, robustness, and the quality of generated trajectories. Additionally, iterative self-improvement experiments are conducted to assess whether further improvement can be gained from subsequent rounds of self-improvement. The paper provides detailed insights and analysis based on the experimental results to validate the effectiveness of the new techniques for self-improvement in enhancing the performance of agent models on complex, multi-step tasks like web agent tasks.
What are the specific results achieved by fine-tuning on synthetic data mixtures in the experiments?
Fine-tuning on synthetic data mixtures in the experiments resulted in significant improvements in agent performance. The best-performing mixture, Mixture B, demonstrated a 31% relative improvement by completing 18 more tasks correctly. Training on all mixtures A, B, and C showed self-improvement on at least one metric, with Mixture C showing a gain in the capability score. Additionally, fine-tuning on mixtures A and B improved the capability score equally and led to the largest net acquisition of capabilities, demonstrating 5 more capabilities than the base agent model, a 24% relative improvement. All agent models acquired new capabilities through self-improvement, with some models demonstrating unique capabilities not seen in other models. Furthermore, the experiments showed that fine-tuning on mixtures A and B did not degrade the quality of generated trajectories, and even showed small improvements towards the reference on the vertex_text DTW score. On the other hand, training on mixture C degraded the quality of generated trajectories from the reference, producing longer trajectories and more invalid actions compared to other mixtures.
What are the limitations or drawbacks of the iterative self-improvement procedure discussed in the paper?
The limitations or drawbacks of the iterative self-improvement procedure discussed in the paper include the finding of diminishing returns to successive rounds of self-improvement and training on synthetic data. While the agent model after a second round of self-improvement outperforms the base agent model, it does not perform any better than agent models with a single round of self-improvement. The analysis of the set of plausible trajectories in the second round revealed that more synthetic training examples can be collected, but they are of lower quality and contain a higher proportion of failed trajectories. This indicates that the quality of the synthetic data decreases with each iteration, potentially reinforcing incorrect actions and biases of the underlying model. Additionally, the paper mentions that the reliability of the evaluation of trajectory quality is limited due to the lack of human reference, which could affect the accuracy of the assessment.